Her question was, have we done step 2 and step 3 yet? Because it seems like we're spending an awful lot of time after step 1. And Laura's like, yes, we are. Get on with it already. And the answer is no, we have not, because I was trying to set up what you're about to have done for you in every single way is step 2 and step 3 automatically generated for you by the machine. I just want you to make sure you understand when that number pops out, why it is what it is. So right now, we have a fairly good belief based on these computations that we have up here. Based on the fact that the standard error of our sampling distribution is about 1.2. So that's 1.2 IQ points. Every 1.2 IQ points you drop, you're dropping one more standard deviation. So outside of 100 minus 1.1, 98.8, you're still within 2 standard deviations. You drop again, 1.2 more points, now you're down 2.4 points. Now you're getting outside of 2 standard deviations. Now I'm using the standard deviation percentages from a bell curve. Ish, they're about the same. Ish, they're about the same. Clearly, we're down 5.5 points. 5.5 points. That's outside of 4 standard errors, if you will. So we know we're going to get significance here. We know we're going to get significance. The question is, do we have to go through this every single time? Of course not. Of course not. What we're going to use this guy called a t-test. A t-test is one of the most popular tests in all of statistics. And we're going to see it over and over again. We're going to see matched pair t-tests, 2 sample t-tests. This guy right here is a single t-test. There's lots of different variants of them. So what we're going to do is I'm going to come over here. I'm actually going to erase... No, I'm not. I'm going to put it right here next to it. Just make sure we're swinging this over so we can see it well. I'm going to zoom in. All right, here we go. There's the screen. Okay, so go to your stats. Your stat menu, over to tests. And this one's so important, it's right at the top. T-test. Well, it's actually at number 2. What did I tell you about anything with a Z in it? Do you remember? Well, anything with a Z, you're only going to use any of these things in this menu with a Z if what other 4 letters are also in there with it? Prop. Yeah, this Z test up here is bogus. Let me show you why real quick. Don't ever go to it. I'm going to go to it real quick to show you why it's bogus. A Z test is the equivalent of a T test. What in there makes you realize it's bogus right now? Remember, this is an inferential test based on you're trying to find out something about a population mean. So what in this test is bogus, and why would we never use it? Why would we never use it? What do you see? What do you see that just makes my hair stand up on the back? It makes me say that again, Michael.
Testing the full population.
Well, that's okay. I don't mind doing that with a sample. I don't mind testing that. But I am appalled that they're asking me to test the population average, but asking me to give them what? What's that? What's that right there? That's the standard deviation of the population. In order to have the standard deviation of a population, what do you have to have already? The population average. How the hell can we claim to not know about the population average if we have to have the population average to get the population standard deviation? I sense you're not as pissed as I am about this. That's okay. This is why we never run z-tests. Because z-tests are fictitious. They go in assuming the population standard deviation. That's ridiculous! You'd have to know mu to do that. But we don't know mu, that's why we're testing. Man. You see why you don't see why, because it's okay. It's alright. This is why we don't run anything Z unless it says prop as well. Now, some of you might be wondering, okay, I don't get it though. There are Z's and there are prop Z's, and they could not be more different. They have the same letter Z, but they are 2 totally different things. Anything Z with a prop is testing the discrete binomial data. It's testing discrete binomial data. Anything Z without a prop is testing continuous data fictitiously. That's why you never ever run anything Z without a prop attached to it. And there's just as many of them that are bad as them that are good. You'll see 2 prop Z test, 1 prop Z test, 1 prop Z in, 2 prop Z in. And you'll see 2 SAM Z test, Z test. You'll see all kinds of ridiculous crap without prop. Just ignore it. I wish I could get in there and just erase them for you, but I don't know how to get in there and do that. Anyway, we go to a t-test. Yes, we go to a t-test. And this makes me happy. Because it asks for one of two things. It either asks for data or it asks for statistics. We have our stuff in data, but if you would, scroll over to statistics and press enter real quick. You'll notice that if you ran one bar stats with me, you'll have these numbers in just like I do. I like this. Nothing here is fictitious. Nothing here is fictitious at all. Everything here is what our data shows. Yeah. Everything's fine. That's exactly, we have a sample standard deviation, a sample average, and a sample size. That's exactly what you get from sample data. It doesn't ask for fictitious crap that you don't have a population parameter. I'm going to go back over to data real quick, just because that's where our stuff is, and generally you won't run one bar stats first. Generally you'll just go straight to this t-test. I'm going to change mu naught to what? What do you think we're going to change it to, Lindsay? Go ahead. Say that again, my friend. Yeah, exactly. It's going to be the 100. You have to tell it where to center your curve. This is why I have you write down the hypotheses so you know what that number you're testing against is. So you're going to have 100 right there. This tells it, I know I have a t-curve, but I got to slide it back and forth until I lock it where it needs to be centered on, which is the 100. This makes a big difference. This is going to change the result of your p-value depending on where that center is. Beautiful. Your list is in L1. I'm going to change frequency to 1 because it's just raw data, as Amy said before. Make sure you're not getting, who's getting a Y when you try to change your frequency to 1? Oh, good. We're past that already. Good. Good, good, good. Last but not least, we come down here. In one prop Z testing, this step said prop, and it had a colon. Prop was the symbol for the little p that we were testing against. Now the TI is wonderful in this respect. They put mu right there, which is exactly what you're trying to test against. So mu, and all you've got to do is pick the correct sign, whether it's a two-tailed test or one of the two one-tailed tests. And we do have a one-tailed, and it's already, in mine anyway, it's already correct at less than, because that's what we're trying to see. Is the average IQ of those suffering acute head trauma less than mu naught, which as Lindsay correctly told us was 100. We think it is based on our standard error calculation. Let's find out. You can go to calculate or you can go to draw. I personally like draw. I like it because it... Sorry, plot 2. Plot 2 caused that problem. Nothing to do with us at all. Something from left over from yesterday. There we go. Here comes my curve. Now, I'm going to pause it for a second. If I expect to see area, where is the area going to be? Remember, the area that it shows us, the shaded area, is the p-value, correct? If I'm going to see area, where is that area going to be? In the tail, right? In the left tail. Okay, go back and broke it instead of just... There we go. So if there's an area, I should see area down here. I don't see any area down there. Which means either, number one, it's off the charts, and or it's so far down that the area is not represented by the pixels. Do these numbers sync up with our argument from before about standard error? How many standard deviations down are we? 4.5. Danielle, your question has been answered. The t-test statistic shows that our sample data, our sample result of 94.5 IQ points is 4.5 standard deviations below where it should be, assuming that the IQ hasn't changed. The p-value, it's not really 0, but it's essentially 0. It's so small that it's coming back as 0. Make sense? You guys buy that logic? It's not really 0. It actually has a value. There is area shaded down there. It's just that the area that is shaded down there is -1, -2, -3, -4. It's down here. Here's -5. That's right there where our data landed. That's where our data landed. So is it likely that our data is a part of this curve? Is it likely that no. It's possible but not probable, not likely that it's a part of this curve. It's more likely that that data is the part of some other curve that's centered down here. Assuming that the data point we saw was not an outlier. Assuming that, of course. Assuming that it's not an outlier. We have a test statistic of t equals -4.5. Let's swing this bad boy over here. and that's actually not bad. We have a p-value, big P, that's essentially 0. So as far as belonging on that null curve, I don't think it does. You can now look at the curve we drew before. Here was 100. Our sample data was 94.5. Where did it land? It landed way the hell over here. Somewhere over here. Off the chart, so to speak. Off the chart, so to speak. 4.5 standard deviations down from average. So what do you think for as far as the conclusion goes? Does it look like IQ has been lowered? It sure does. It sure does. It appears that the average IQ has been lowered after acute head trauma. It appears that it's been lowered after acute head trauma. Is that believable? You guys buy that? Ask me questions if you have them right now. Ask any questions that you have. Any concerns that you have with the data. Liz, go ahead. Oh, invalid dim. Probably the same thing happened to me. You've got a plot turned on. It's probably causing the issue. So we'll just do that. Anybody that gets that invalid here, okay. Here she comes. The invalid dim error that I got before, that often happens when you're trying to grab. I'm going to have you guys grab some data right now, actually. And if the problem is if you leave a plot on and you remove a data list, it'll try to grab something that's not there anymore. It's not smart enough to turn itself off. Unfortunate. Any concerns? Anything we should be concerned about? This is a bit of a loaded question because it's very, very specific to something we talked about a lot in 243. Kind of really haven't mentioned a whole lot yet. I brought it up with T intervals, but I didn't get too far into it. Anything we should concern ourselves with since we're talking about averages instead of proportions? When do averages misbehave? When do averages misbehave? When do averages misbehave? Mimi?
When you have outliers.
That's something you need to be concerned about. Thank you. If you have outlier data, your average can be artificially moved towards the outliers. And therefore, you might be getting a distorted view of what's actually going on in the data set. I'm not doubting that the average of this data set is 94.5. I'm just questioning whether I saw some really big data values in that data set, 124s, 117s. I also saw some pretty small ones, 86s, I think, or 84s, or something like that. And part of me is like, oh, maybe we're getting the average of whatever it was, 94.5, but if that's being pulled lower by outlier data, there's a possibility that the average is artificially low. You see what I'm getting at there, friends? So let's do a quick check of the data using a histogram and a modified box plot and see if anything is maybe making the data misbehave. Okay? So this is a throwback, of course. This is a throwback to 243, but it's a good throwback to 243 because we don't want to publish our results. I'm going to erase this now. Guys. We don't want to publish our results on fraudulent data. And I say fraudulent, I don't mean intentionally fraudulent. You might not be intentionally fraudulent. It might just be that your data is becoming skewed in a way that you're not particularly looking for, especially if you're excited because you got good results. All right, so I'm going to turn two plots on. Two plots. Plot one, I'm going to make a histogram. Here's why I was getting my dim error before. I was trying to graph L1 and L2. I only want L1 and 1, not L1 and L2. And I'm going to turn plot 2 on, and we're going to make that a modified box plot. Why modified box plot? Oh, sorry, Liz, go ahead, ask that question.
No, I was just...
Okay. Why modified box plot? What will it show us? It'll show us outliers if there are any, using an IQR. So if I take a look at the overall stat screen, I've got my histogram turned on my raw data, and I got my modified box plot turned on my raw data. I got frequency set at 1 because I want that, because I just got a list of data in there, so we're happy. This way I'll get a histogram and I'll get the box plot. We'll see if there's any outliers, and then we can adjust our data set if necessary to see results. All right, so I'm going to do a zoom, stat. There's my histogram, there's my box. We have some outliers. I'm going to play a little bit with the window because the box plot's sitting on top of the histogram. I'm going to kind of mess with it a little bit so it's not sitting directly on top. And I think I can do that by just changing this. If I make this 70 and I make this 130 and I scale it by 5, that might do it. Yeah, that did it beautifully actually. There's my data. Look at my data. Now, the t interval. You might remember this from back in the day, you might not. It's okay if you do or if you don't. Back in the day, there were some assumptions we had to make about our data. There were 3 of them in particular. 2 of them I don't care too much for because they're not that important. One of them I kind of do. The 2 that I don't care too much for, remember the magic number I mentioned in 243D? There's a magic number of data points that you should use before the second length theorem kicks in. Remember what that magic number is, friends? 30. Good, 30. If you don't remember it, that's okay too, because I don't care that much about it. I honestly don't care that much about it. Nobody's proved why it has to be 30. No one ever has proved why 30 is important. All I ever noticed about 30 is that's when the t and the z curves line up pretty nicely with each other. I'm like, oh, there we go, yay, happy. But nobody's proven that 30 is gold. It's just become this lexicon of, yeah, whatever. So 30, yes. I don't care that much about that, though. One thing I care slightly more about, is the data should be roughly bell-shaped and symmetric and unimodal. So not a whole lot of skew, basically a bell shape. Is our data roughly bell-shaped? It looks pretty damn good to me. I don't care about that much, because you can still get pretty far away from a bell curve. You'll see this on your project on Thursday, by the way, just so you're wondering. You can get pretty far away from a bell curve and still have a good estimate. The one I care about are the outliers. Those are the ones I care about, because those are the ones that truly pull an average. We've got 2 outliers, yes? We've got 2 outliers. I'm going to hit trace. I'm going to jump up to them, and I'm going to take a look. The outliers are the 117 and the 124. The 117 and the 124. Okay. Should we be concerned about our result based on those 2 outliers? And this is kind of like an AP question. It really is. Should we be, actually shaking your head no. Nice. We do not have to concern ourselves about those 2 data points. How come? How come? And this is definitely an over and above kind of question. Why do we not have to concern ourselves about those outliers? I just got done saying that outliers can artificially pull your average. And then I backpedal and I say, but I don't care about those 2 outliers. Why do I not care about those 2 outliers? To give you a hint, look at the claim we're testing. Look at the claim we tested in this test. We were testing to see if IQ scores were lowered. If anything, what are those 2 outliers doing? They're pulling the sample average higher. So we got a significantly lowered IQ score, even with the presence of high outliers. If I was to exclude those from the study, what would happen to our result? Would it get less significant? It would get more significant, wouldn't it? Because our sample average would drop even further. That 94.5 is being pulled up by that 117 and that 124. If I took those out of the study and re-averaged, the 94.5 would drop even lower, which means we'd go down even further standard errorly, and we get even more significance. That's why I don't care if those outliers exist. They're not influencing my result at all. As a matter of fact, it's proven the point even more that we can have 2 high outliers and still have a significant result. Does that make sense? You guys buying that? You can say no, of course. You can say no. In general, when you're outside of the academic walls, you want to watch for stuff like that. You want to watch that outliers aren't causing your results.
That didn't necessarily mean that they got smarter after getting it. You don't know their original IQ before that, right?
We're assuming they all had an average IQ beforehand. Now, and again, IQ is one of those things that is often used in tests to measure intelligence. And I've got a humongous problem with that anyway, the whole idea of intelligence being measured by a test that favors those that are good with pattern solving and mathematics and recognition. I routinely test ridiculously high on these things. And I mean, look at me, I'm on a bare feet for God's sake. You know, I mean, I don't think there's much of a tie between smarts and these test results. However, the assumption is these folks had an average IQ before they started. Now, granted, we expect, where's 100 on this? Let me just check real quick. 70s by 5. So here's 70, 75, 80, 85, 90, 95, 100. Okay, there's 100 right there. So you can see that 75% of the box plot is below 100. pretty good indication that the IQ is below 100. 75% of the box plot's below 100, more than half of the bell curve is below 100. Pretty good empirical evidence that, at least in the sample, it's dropped below. Then we adjust it for maybe standard error, and we're even happier about the result being below 100. So, yeah, that's why I'm not that concerned about these two guys over here. They're in the top 25%, and they're kind of outside of the typical top 25% anyway. Is that fair, Michael? Great question, great question. Other questions? We didn't have to worry about testing for outliers with proportions, because proportions are testing essentially medians, if you think about it that way. You're testing percents or percentiles. Percentile just says, oh, that's the highest data point. The 124, it's just the highest data point. It doesn't matter how far away it is from the next highest data point. It's the highest, the next one down is the next highest, and they're equally spaced. That's why you don't have to worry about that kind of a restriction on percentages. Laura, did you have a question? I thought I saw a question coming in and I started talking, I apologize.
Not really, but now that you ask.
Go ahead, please.
When are there ever non-outliers?
Well,
I'm gonna guess with a giant data set or something.
well, actually, the larger a data set is, the more I'm willing to believe there would be some. And here's why. As the data sets get larger, if they follow a certain shape, like a bell curve, the variance is going to drop. This happened in my 243 class yesterday. Remember I asked you guys to guess my height last year in 243? And we almost got a perfect bell curve when you guys did it. Yesterday, when I asked, I got a bimodal, I got a perfect bell curve followed by a spike at 73 inches. And then a 74 and a 75. There were a whole slew of outliers based on that. But I think that was just because there were only 23, I think, responses. If I collate that with everybody else I've ever asked, it's going to smooth into a perfect bell curve. So with large data sets, I expect actually more outliers because the standard deviation tightens up as you get a larger data set. There's less variance on average. Now, there are always extremes, the highest and the lowest. The question is, how far out do they have to go to be judged an outlier? And that varies depending on the size of the data set and the measures of the standard deviation in the interquartile range. So, I love what you're saying, but believe it or not, I actually expect them more on smaller data sets because of that. And now, I say that, of course, I'm going to edit that statement by saying I found a very interesting one a couple days ago. I sat in a writing class, and I don't know if I told you guys this about the caffeine drinks. Did I tell you about this? Maybe I did. I did. I actually tracked the data set down. The data set had 575 data points in it. That's huge. 575 energy drinks that were on the market the year the study was done. 80 of them were termed outliers by this method. 80 out of 575. So roughly, what is that, 1 in 6 are outliers? That's crazy to think about, right? That's crazy to think about. But that's when you look at the data set and you go, maybe I should have two different data sets. The high caffeinated drinks and the low caffeinated drinks. Because they came in clusters. There was a beautiful bell curve of drinks on this side that were between 0 and 50 milligrams of caffeine per fluid ounce, which is like a cup of coffee-ish somewhere. No, actually not, it's more than a cup of coffee, but it's low. It's low enough not to be like poisoning your liver. There was a bell curve, then there was a hump, a little hump, bump, bump, and it just kept going. It was comical. I was in a room in Grandview. I had to have 5 kids help me draw the box plot for it. Because I had them run down the side board. I handed a marker back. Keep going, keep that tail going, keep that whisker going. And then when we modified it, the box itself was like this big, and then it was all the way down. Crazy amounts of outliers. So a better answer to your question, Laura, is actually this. It depends on how you define it. It depends on how you define it. And there are half a dozen ways to define an outlier. This is only one, using interquartile ranges. So I expect them more on smaller data sets. That doesn't mean you can't get crazy ones like I did with the caffeine levels. Thank you. Will, go ahead.
So for that caffeine level,
yes,
that variation would be kind of captured with the standard error.
If you were the trick with that one was I treated it not as a statistic but as a parameter because the study's claim was this was every caffeine drink on the market. So in other words, I had everything. I didn't have to worry about a standard error. Does that make sense?
If we had a sample that looked like that,
whew, I'd have to capture the standard error, right?
And so. And the t-test has got that integrated in it, right?
Right, but that's where I would look for a different test. Okay. At that point, I would say, holy crap, look at this data. Can I even talk about an average, right? Can I even talk? The reason I was drawn to the test was that the person in the paper was talking about the highest level of caffeine drink in the study. So they were using an outlier to describe their mean. I'm like, that's bad. That's bad regardless of whether it's a sample or a population. But then when I got in and looked at it, I'm like, holy crap, this is really interesting. There's some really cool stuff going on. But because of the discussion we just had, I'd be concerned using a t-test on this. I would go to find what are called non-parametric tests that don't assume it's bell curve, don't assume it doesn't have outliers. We'll get into those later in the course. I'll have you guys do some of those on your last out of class exam. Is that a fair question? I hate to push it back, but this is the kind of the thing of running the assumptions, running the checklist is, should you even do this? Here's a t-test, should you do it? Here's the one problem C, should you do it? Sometimes you say no, and you run other tests. I wish we had more than 10 weeks together, I know you don't. But if we had like 20 weeks, we could have a whole non-parametric back half of the course. But we don't have to have 10. So I do the more common parametric ones with you guys. Is that fair? It's kind of a sidestep of your question, unfortunately, but it has to be, really, at this point. We'll get to more, I promise. Laura, your question answered okay?
Okay, so
Go ahead. No, go ahead.
Smaller population or smaller sample size has more outliers?
On average, that's what I notice. Because there's more variation on a smaller sample size. What you're going to see, not to look forward again, in your last project was on linear regression. That's when you actually have bivariate data, like you're trying to correlate, for example. If I look at the guesses that students did in 243 when they guessed my height and guessed my weight, and try to correlate to see if there's any kind of relationship. Maybe the people that guessed me taller also guessed me heavier. And I plot those in a scatter plot and I try to see if there's any kind of predictable trend in that. If you look at small data sets, you're allowed more variance in the data between them than if you have a larger data set. The idea being a larger data set, the trends are going to be more clearly shown, but in the smaller one, because of the random nature of sampling, they're going to be more scattershot, until the trend begins to kind of show itself. Because if there is a trend, and this is the if there is a trend, on average, more of the points are going to land near that trend, but in a small data set, maybe you haven't seen enough to get most of them near the trend. Is that fair? So by definition, the measure of standard deviation, whatever you're using, has to be larger on a smaller data set, assuming there's a trend to be found. That's why, this is my mathematical reasoning as to why I expect outliers more in smaller data sets. And it seems to work out pretty well that way, because the standard deviation's tightened down. This, you can see it, actually, here's a great example. You can totally see it whenever you guys forget to run one var stats. We're going to do it right now. We'll do it right. The next little data set down here. When you run one var stats on a group data set and you forget to put L1, L2, the standard deviation usually goes down when you put the L2 in, because there's less variation on average around the average. We'll see it here in a minute. So, but that's why, and mathematically it makes sense as to why it has to shrink. Fair?
Yeah.
Okay, we'll come back to that. It's a great question, Laura. Thank you. All right, let's stop this.